I dare say you all out there know what that is at the top of the slide. Garbage in, garbage out. Always true when you're using a computer. And no simulation model can be any better than its input data. A simulation model that's built on estimated data, and that could very well happen. A very good time to build a simulation model is when the process being simulated is still under design on the back of a cocktail napkin, as the saying goes. But then the data is going to be estimated and very approximate. So the results of the simulation model will be very approximate estimates. That may be far better than nothing at all. But conceptually, think of it as a minimum. The quality of simulation results is the smaller of the quality of the model building, and that's many other webinars, and the quality of the input data. And keep in mind that a simulation model that is completely wrong is worse than having no model at all. The completely wrong simulation model can very well lead management decision makers right down the primrose path into a disaster. So input data, it's worth spending time both getting it whenever possible, and very often getting the input data can occur concurrently with building the model, putting the input data into the model as the model building is underway. That saves a lot of time. And not just getting the input data, but spending time to analyze it statistically in order to best represent it in the context of a simulation model. Now, here's some typical questions to think about. Do you have exactly the right data? Now, the first bullet point calls attention to a potential misunderstanding about time units. That would certainly lead to a disaster. Second bullet point, maybe plant X is not yet even built. So the input data will be estimated. The cycle time of the machine in the other plant down the road or in the next state may be a very useful approximation as a preliminary estimate. But the fact that it is an estimate should be documented. If we're running a job shop, what's tomorrow's schedule? Maybe we don't know yet. Maybe the boss hasn't decided yet. Maybe the input work orders aren't even here yet. Well, we can model using today's schedule or yesterday's schedule to see what happened. If we run the model using yesterday's schedule, does the model act the way the real system acted yesterday? That can be a very valuable technique for validating the innards of the model. Model needs number of demands. Well, we probably do know how many items we sold. Maybe more were demanded. Maybe we should be asking how many stockouts and unhappy customers walked away. The model needs the number of parts riveted. That's a common type of example. Well, we might know how many pallets we riveted. How many parts are on a pallet? 5? Is it always 5? Is it true that a pallet cannot possibly contain more than 5 parts? Does every pallet have 5 parts riding on it, or a few have only 3 or 4? So for all of these and many more, The best prevention of horrible misunderstandings is a nice long shop talk between the person building the model and the person who wants the model, like the client, the expert on the real system and how it works or is going to work after it's built. And if not, what do we do about it? Well, you might be able, if the plant currently exists, maybe that's the reason we're simulating. We have a plant already in production. It's not producing enough. Production is too expensive. Inventories are too high. All sorts of problems. The natural thing to do, and the best if it's possible, is go there and collect exactly all the data you need. Now, if that is not possible, and in the long run, it probably is possible, but would it take too long? A wonderful simulation model using exact data that's completed in October is no good if you need to make the decisions by August. You'd be better off with an admittedly approximate model completed by August so the results can be looked at and used to guide management decisions while there's still time for management to make a decision before the commitment has been made. And that's what the extrapolation refers to. Now, very frequently, and this has occurred often in my 40 years of experience with simulation, about half of that 40 years was with Ford before I came to PMC. Here's how conducting a sensitivity analysis might work. And this is a scenario I've been on more than once. The old machine has 5% downtime. And we know that, we've observed it, we've collected the downtime. How long between times the machine breaks down and how long it takes to repair the machine. And the salesperson is claiming much better reliability for the new expensive machine he or she is hoping we're going to buy. So the first thing we do is conduct a sensitivity analysis. We build a model of the plant as it is now and run it to validate the model results against what we see in the plant. And that model of the plant as it is now has 5% downtime in that machine. After the verification and validation, and by the way, that's a whole nother webinar, we conduct our sensitivity analysis. We go to our model and change the numbers that produce 5% to numbers that produce 2%. And one of the nice things about simulation is that's quick to do. Probably takes about 10 minutes. And run the model again and compare. Now, the model with the hypothetical new machine in it may produce just about no more what the old model did. Well, that would tell you the model is insensitive to the downtime of that machine. And insensitive, that's where this term sensitivity analysis comes from. So we don't need the new machine. We probably need to correct bottlenecks and difficulties elsewhere in our production process. So it was a nice lunch with the salesperson and we say thanks, but not right now. Now, on the other hand, and this also happened many a time, 2% downtime, the throughput is much more, bottlenecking is much less. Certainly, the sensitivity analysis is telling us we're going to benefit greatly if we have that new machine with 2% downtime. So we tell the salesperson what our model told us. This 2% downtime is really important to us. And our lawyer says, let's insert a contingency clause in the contract proposing a penalty if we buy the new machine and it does not live up to that expectation. And salesperson number one said, "Oh, I have to go. I have to go back and talk with my boss." And by now, the salesperson is underneath the conference table. Well, we haven't bought the machine yet, but we have interesting information. Salesperson number two at a different company says, "Yes, we'll agree to that. My boss told me we can. We've torture tested the new machine under extreme conditions of temperature, humidity, contaminants, and so forth. We're confident in it, and we will negotiate that clause with you." Well, now we know which supplier to buy from, and that's good knowledge to have. That's how a sensitivity analysis might work. And indeed, I've participated in some that went just about like that. Now, if you have no data at all, and that could well happen if you're modeling a system that's still under design. And in terms of potential ROI, the benefit to cost ratio is characteristically largest, typically 10 to 1. I've seen 80 to 1, 90 to 1 over my 40 years. But then you have no data at all. Well, you can ask an expert. There's always an expert available at a price. You can do the sensitivity analysis just mentioned. You can use statistical distributions that are theoretically justifiable. And indeed, that's one of the, how do you know what to do on the second half of this slide? That's part of the consultation statisticians at PMC are ready to provide. And then you admit that your model results are approximate, but they may nevertheless show that alternative A for designing the new system is enormously better than alternative B. With your approximate data, maybe both results are wrong by 15%, but they're still in quality order, and that's extremely valuable information to have. Go with alternative A. Now, there's what some uniform data might look like. And we encourage, when we're working with our clients, here's the example of a distribution we're thinking of using. Does this make sense to you? That type of communication, as the model building process goes along, is extremely important in building model credibility. First, the model has to be verified. Is it debugged? Then it has to be validated. Is it an accurate reflection of the real system? Then, step 3, it has to achieve credibility with the person responsible for using its output to make decisions. If the model does not achieve credibility, it's not going to be used as guidance for making decisions. So why on earth did we bother investing the time and money building it in the first place? And frequent communication, nice long shop talks between the people building the model and the people who are going to be guided by its output is absolutely essential. Another thing we always do to make that happen is document the model very thoroughly, both inside and outside. Inside the model, all simulation software nowadays has places to put commentary. We make sure that gets filled in. Outside, there should be a technical report on how the model was built, how the input data got into it, how the input data were analyzed, like picking one of those distributions I just clicked through, and where the input data came from, and when, so that it can be updated and modified as more input data become available. Now, what statistical questions do you need to look at relative to your input data? One is autocorrelation. And I deliberately put this one first because it's the one, in my experience, most in danger of being overlooked. Now, here's an example from a project I actually worked on. We were modeling one of those drive-through oil change places. Everybody driving through wants an oil change, and some of the customers driving through also want a transmission fluid change. So gather data on how long it took to drain and change the oil. That's one observation. Gather data on how long it took to drain and change the transmission fluid when that was done. The oversight that's likely is simply fit one set of data to a distribution, put that aside, fit the other set of data to a distribution, and put both of those in the model. Now, the model is not going to bring up a big warning window, but that procedure represents a tacit assumption that the two data sets are independent. Oh, let's take another look at that. I said, just based on experience, is it likely that a car that needs longer to drain and change the oil needs longer to drain and change the transmission fluid? Maybe both tanks are bigger and take more quarts. And we did indeed find autocorrelation, positive autocorrelation. And as is typical, putting that autocorrelation into the model confirmed that the original predictions without the autocorrelation on throughput, total customers served, were over-optimistic. Positive autocorrelation typically makes a system run slower. Now, I hope this never happens to you. Don't let it happen. We went back to our original data and looked at the side-by-side pairs of oil change time and transmission fluid change time. We had them side by side in time order of customer arrival. The nightmare is, oh, we don't have them side by side anymore. I sorted those data top to bottom and threw the original data away. Well, it was about then in the middle of that bad dream that I fell out of bed. But don't let that happen to you. Never throw the absolute original data away while the project is still alive. You would lose that ability to test for autocorrelation over time. Are the data time dependent? For example, the night shift is less desirable. Workers with seniority choose not to work on it. So the newer workers work the night shift. They're less experienced and less adept, and their cycle times on manual machines are longer. Travel time may take, in a big supply chain, travel time like trucks between warehouses may take longer in winter when there's snow-covered roads. So check your data for time dependence as the simulation analysis proceeds. Now, did you get any really, really long repair times? How long and skinny is the tail? Maybe you've collected 20 or 30 data points. That's usually enough to make a good approximation for what distribution to use. For example, time to repair a machine. Now, was one of those data points the time that you didn't have the replacement part in storage and had to order it? And related to the autocorrelation, sort of a loop between the last bullet point and the first one, are observations gradually changing with time? Cycle times getting longer as the worker gets tired. Cycle times getting shorter as the worker learns the task and learns little tricks to do it faster. So those are examples. You don't just take input data and shove it into the model. It needs to be looked at statistically beforehand. And there's plenty of statistical tools on our desktop to do that looking, plus the statistical knowledge required to do the looking. Now, here the modeler has a choice. You can tell the model sample directly from the set of data points I collected. Or, preferable, you can use a statistical technique. There's 3 well-known good ones listed here in the diamonds to find a good fitting statistical distribution. I just clicked through 3 of the basic ones: uniform, triangular, beta. There's many others: Weibull, gamma, log normal, exponential. Now, you may find that your distribution, your original data, is bimodal. That's a fancy way of saying it has 2 peaks, 2 humps, like a camel. Then I can practically guarantee you that you won't find a good fitting theoretical distribution. What you should do if that bimodal appears when you look at a histogram, maybe I didn't know it, but I was really collecting 2 data sets. I carefully collected lengths of repair time to get a machine running again. I didn't know it yet, but the repair time, some of them were for one type of failure, and some of them were for another type of failure. I should subdivide them and have another look. Or I was collecting data on cycle times as this manual operation. I didn't notice it yet, and the user didn't think to tell me, and I didn't think to ask the user, oh, maybe that machine is operating, doing its work on 2 or 3 different types of parts that come down the production line in random order. And it just naturally takes more time to do the work for a model A than to do the work for a model B. Then I'd better subdivide my data set, and I also need to find out what % of our production is model A versus model B, and I'd better know as the simulation runs, each part arriving at the machine, is it an A or a B? So no, we don't just stuff the data into the model. Now, how shall we run the model? That's an input question. It's more than clicking a button. Is the system terminating or steady state? Well, what do those terms mean? A terminating system might very well be a bank or a restaurant. It opens up empty and then closes at the end of the day when all the customers leave. So in real life, the bank opens up empty. The simulation model starts running empty. That is a terminating system. On the other hand, Many systems, an emergency room or a very busy airport or a typical manufacturing line, is likely to be steady state, never closes down and opens up again. In a manufacturing process, we might stop work Friday afternoon, but Monday morning we start again with the system already full of the parts that were there the week before. Those are steady state systems. They typically do not start from a completely empty condition, but the simulation model does. So the early results during the simulation run will be biased, and we'd better get rid of that bias. So simulation software will let us specify a warm-up period. How long does it take the real-life system and the simulation model condition to match at a typical long-run typical condition? For example, it might be necessary to run the simulation model for a day until it reaches long-run typical conditions. So we have to tell the simulation software, use the warm-up period of 1 day or 1 week, whatever is necessary, throw those statistics away because they're biased, and then run it for a good while to get our typical long-range KPIs, key performance metrics. Now, if I go in the simulation model and put some material in some of the buffers to initialize it, maybe I don't need quite as long a warm-up time. Now, I guarantee you'll need more than one replication. A simulation run is an experiment using random numbers that will be generated to match the randomness in the real system. Randomness of cycle times, randomness of how often a machine goes down, randomness of how long it takes to repair it, randomness of arrivals, randomness of demand, and so forth. There's randomness all over the place. And one of the great talents of simulation is its ability to model randomness. And to model it and build confidence intervals, any statistics book will tell you you need a sample size of more than one. In many studies, it's 10 to 30 replications in order to build confidence intervals for your key performance metrics. Now, the 4 bullet points on this slide represent different types of inference that the decision maker may need for the model. The contrast in the first bullet point is very common. If it's qualitative, the simulation results need to be moderately exact. If it's going to be quantitative, will we meet our contract obligation of so much throughput per hour? And at what confidence level? 90, 95, and 99 are common. Those are going to affect how accurate the data going into the model has to be. And occasionally, when there's a lot of alternatives to explore, the desired output from the model, less commonly, is going to be one of the last 2 bullet points on this slide. Now, we've got 3 examples coming up. And here's the first one. All of these are projects I've worked on. A factory that made sunglasses, not prescription ones, but the ones you can just put on. And largely that factory was manual operations. And for this project, we had to collect all of the manual things listed and some others. This is not a complete list, but it gives you an idea. The fifth one, what was our model mix between models of sunglasses? Transfer times between one operation and the next. If a worker carries a tray full of sunglasses, that represents a transfer time. Reject rates. We've already talked about downtimes, closely related, but not at all the same. The workstation, machine, whatever it was, it didn't break down, but it introduced a defect, and then we have to either throw that one away or maybe send it to a special place and we can repair it and put it back in the line. And all the data pertinent to that needs to be collected, analyzed, and put in the model. And the very first one is the most obvious one. So that's what you'd call the cycle times. What about the third one, the changeover times? If I just made model A and now I'm going to make model B, I might have to adjust my workstation, like resetting gauges, for example. That takes time. If I make long runs of model A and then long runs of model B, I'll spend less time on changeover. But I'll have greater danger of a huge inventory of model A and a stock out of model B. There's a sweet spot in there. What should my lot sizes be? And simulation is very good at finding that sweet spot. One of the common usage of simulation. So a lot of communication. We use the distribution fitters, and very often people like this import the data from Excel into the model, and likewise, that's next week's webinar, output the results from the model back into Excel. That was one project. Here's a different one. A typical flow shop. Well, you sure needed the cycle times again. And in this particular case, which was not true in the sunglasses factory, we had work cells and there were changeover here. And unusually, this was a terminating simulation. The client wanted to know, under certain conditions and certain criteria of a rush job, how long is it going to take my system to finish making it so that I can negotiate with my client? And very often you need to model travel times with people moving around, either because they're carrying parts or they're walking from one machine to another to repair the machine or do work on that machine. Or in healthcare, that's a big area of simulation now, to escort patients in wheelchairs from one part of the hospital or clinic to another. And in a warehouse, this is often automatic guided vehicles or forklifts. What routes will they travel? How fast do they travel? And so forth. So a great many simulation models need a lot of detail on travel time. Well, a third example, rather a different one. And in this case, our client had a lot of the current data needed. And this particular project was also a good example. Simulation is most powerful, not when it's all by itself, but when it's used in conjunction with other, i.e., industrial engineering techniques, such as ergonomic analysis for the benefit of the workers, value stream mapping, process mapping, Six Sigma, and so forth. That's one reason that early on, Brian showed you a slide detailing other things we do besides simulation, because simulation is typically of more benefit to our client when it's working in synergy with a lot of the other valuable things industrial engineers can do. And this was a case where the total project time was shortened. Oh, we need this additional data. We first built the model with no downtime in it at all and ran it. That helped validate it. And it gave the client a number of interests. What is your theoretical maximum throughput possible? And then how much does downtime lower it? How much of a problem is downtime and repair time causing? And that data could be collected concurrently with continuing to build, verify, validate the model in order to shorten the overall calendar time on the project.